Hi, everybody. Thanks for coming back to the Compton lecture series. This is lecture number 7, and time is really flying by. So I'm really excited about this lecture because we're finally going to talk about this picture that I've been showing on my title pages for the previous talks. So we're finally at the point where we have all the tools that we need to understand this detector. So first, I just want to do a little quick review about how we detect neutrinos. So in the previous lectures, we've talked about different ways of detecting neutrinos through different detectors or different observations that we've made. And you can roughly categorize these into two different types of detection. So there's direct detection, where you're actually observing the neutrino interact inside your detector. And then there's indirect detection, where you're actually inferring the neutrino's existence or some properties about the neutrino through a different process where you don't actually see the neutrino. So on the direct detection side, I have some examples from some of these previous lectures. This is an event from the ice cube experiment, which observes high-energy neutrinos traveling through the Antarctic ice. And what is being detected here is a charged particle that's emitting Cherenkov radiation. And that Cherenkov radiation is being detected by strings of photosensors that see that light. Another example of the same technique is in the Super Kamiokande experiment over here, where instead of looking in the Antarctic ice, the neutrino is producing particles that travel through the water. And the same principle applies where Cherenkov light is emitted, and you get these ring patterns that the Super K experiment can see on the walls. There's also scintillation detectors. This one is taken from the NOVA experiment that's running at Fermilab right now. As the neutrino comes in, it emits charged particles, which interact with the scintillator material and produce a flash of light. And you can instrument that scintillator volume and see the tracks of the particles. Another example, a classic one from the Camland experiment, just next door to Super K in Japan, it also observes scintillation light from lower energy neutrinos. So there's lots of ways to do this direct detection. And then we've also talked about indirect methods, where you can look at the decays of certain radioactive isotopes and see how the energy spectrum of the particles that come out of those decays is affected by a neutrino. So in the case of beta decay, you get some shape like this, where if there was no neutrino, you would expect a single energy, kind of like the alpha decays that we talked about back in lecture 1. And then last week we talked about cosmology and how we can look at cosmology for probes of different neutrino properties. So this is a picture of the cosmic microwave background, where we've derived a lot of our understanding of how the universe evolved, and also inferred some properties of neutrinos through measurements of its very tiny fluctuations. So I just want to talk about neutrino interactions again. So when we think about direct detection of neutrinos, what's really happening is the neutrino is interacting and it's hitting some kind of target in our detector. So a nucleus, you could imagine. You have a big volume that's instrumented, and you're watching it for neutrino interactions. Those neutrinos will interact and hit a nucleus and then produce a charged particle. So what we talk about when we talk about neutrino interactions is the weak force. It's one of the fundamental forces that we know about nature. And it has this interesting property where it switches neutrinos of a particular flavor, so in this case an electron neutrino, denoted with this little E at the bottom of the neutrino, into an electron. So that force changes that neutrino into its charged particle, and then we can detect that electron that comes out. It also affects the nucleus. So here, I didn't draw it, but it changes a proton into a neutron or a neutron into a proton. It can change the type of particles that's involved in the interaction. And we can use this to great effect because it turns out for different types of neutrinos, you get different types of particles out of these interactions. So on this side, I've switched the electron neutrino into an anti-electron neutrino, and I'm denoting that by drawing this bar over the top. And now when it interacts in the nucleus, it produces a charged particle of the opposite sign, so an anti-electron or a positron is what we say. And so you can use this phenomenon to design experiments that can differentiate between these particles or these different types of interactions, depending on how you build your detector. Okay, so another interesting feature of neutrinos, and probably the one that scientists have spent the most time trying to figure out, is all about neutrino mass and how that influences this phenomenon called oscillations. So as we talked about in previous lectures, neutrinos are a superposition of different masses, and those masses interfere through a quantum mechanical effect that causes the flavor of the neutrino to change over time. So actually having this picture of a discrete electron neutrino is not totally accurate, because as that neutrino travels through space, what's happening is that its flavor is changing. And so as the neutrino travels, we can look for that flavor change. And so this diagram here is just showing that you have these three types of neutrinos: the electron neutrino, the muon neutrino, and then the tau neutrino. And all of these things are in play when the neutrino is traveling through. Based on the previous page about how the neutrinos can produce these different particles when they interact, you can also design experiments that look for this flavor change. So from an electron neutrino changing into a muon neutrino, you would then expect to see muons in your detector instead of electrons if this flavor change happened. And this is all driven by the fact that neutrinos have mass. We can be a little bit more quantitative about how we describe this oscillation. So when we say oscillation, it really is an oscillation. And we use the example of sine waves to kind of draw out what this might look like. And what is oscillating is not some property of the neutrino, but it's the probability of seeing that neutrino as a particular flavor over time. So I've drawn these two curves here, and each value along the horizontal axis here is a particular value of L over E. So I'll talk about what that means in a minute, but for now you can just think about it as the travel distance, how far the neutrino is traveling. And if you design an experiment where you have a source of muon neutrinos, then you can imagine that when your distance is 0, you have a pure muon neutrino. The probability of finding that muon neutrino is exactly 1. But as that neutrino travels some distance from the source to your detector, that probability starts to decrease. And as that probability decreases, the probability of finding the other flavors of neutrinos increases again. So here I've drawn the muon neutrino and the tau neutrino. The simple picture is that the muon neutrino probability goes down, and then the tau neutrino probability goes up. So if you put your detector at a position around this 500 mark here, for example, you would expect to see about 30% muon neutrinos and 60% tau neutrinos, for example, something like this. And that combination can tell you something about this oscillation pattern and something about the properties of the neutrino masses. So one important feature of this picture is that the frequency is not chosen arbitrarily. In fact, the frequency is set by the difference of the different neutrino masses. So we call that delta m squared. It's the difference between the squared values of the neutrino masses. But you can think about it literally as a frequency of how this probability changes over time. So back to L over E for a second. So what is this? L is the distance that the neutrino travels. E is the neutrino's energy. So it's a ratio, L over E. And if you think about changing E of the neutrino, so you're making either a higher energy or a lower energy neutrino source, that has an effect on how these oscillations happen and where you should put your detector. But critically, this L over E, these are experimental parameters that we get to decide when we build our experiment. So it's the distance L and the energy E. The distance is set by the distance between the source of the neutrinos and your detector. And then the energy is a characteristic of that source. So different sources have different neutrino energies that are characteristic to them. I'll give a couple examples of this. So the first one is the T2K experiment, which we've talked about in previous lectures. This is an experiment where you have a beam of muon neutrinos that starts on the east coast of Japan. And then that beam of neutrinos travels through the Earth's crust all the way to the west coast, where there's a giant detector called Super Kamiokande. And that baseline is about 295 kilometers, and the average energy there is about 600 MeV, or 0.6 GeV. So if you do that ratio, that L over E ratio, what you find is that about 300 kilometers divided by 0.6 GeV gives you a L over E of about 500 kilometers per GeV. So it was no accident that in the previous page I kind of tuned this diagram to put that oscillation picture around that 500 L over E mark, because this is actually what the T2K experiment is doing. They've designed their experiment because we think that the frequency should give you an oscillation maximum around this 500 L over E mark. So this is a real effect. Okay, so that's T2K, but on the other hand, you can have other types of experiments with other types of sources that give you different values of L over E or the same type of L over E. And that lets you really hone in on these oscillation parameters that we're trying to measure. So another example of this is the Diabei experiment operated in China. There's a reactor in China, a nuclear reactor, and then about 1 kilometer away, there's an array of neutrino detectors that see the neutrinos coming from this nuclear reactor. And if you look at the L over E for Diabei, the baseline, as I mentioned, was about 1 kilometer, but the energy of the neutrinos coming from the reactor is much lower than the energy from the T2K experiment. So much lower, in fact, that even though they're only 1 kilometer away, the L/E ratio works out to be about the same, about 500 kilometers per GeV. So this is an example of 2 different experiments that have very different baselines and energies, but they see the same oscillation frequency because the L/E value is the same. Okay, so using all of this, we've put together kind of the modern picture of neutrinos, and that modern picture involves 3 distinct neutrino masses, which correspond to 2 different frequencies. So I'm showing here on this picture just kind of what we understand in how neutrino masses mix with the different neutrino flavors. And the key point here is that these neutrino masses are separated by different values. So in particular, this nu3, which is just a label for the heaviest neutrino mass in this picture, is separated from the other 2 neutrino masses, nu2 and nu1, by some value delta m squared 3,2. And actually, this picture is a little bit misleading because there are 2 ways you could order this, but for the purposes of oscillation experiments, actually only the absolute value matters. So we can pick either ordering, and this would be fine. But anyway, so this delta m squared 3,2 sets one of the frequencies. And then there's another frequency set by the difference between this nu2 and nu1 state, so a second frequency. And so when you build this picture of oscillations, what it looks like is something like this. This is an example from nuclear reactors. On the vertical axis, I'm drawing the probability of an anti-electron neutrino oscillating to an anti-electron neutrino. And because the anti-electron neutrino can oscillate to the muon and tau flavor neutrinos also, that probability is not always 1. So if we have these 3 masses, which correspond to 2 frequencies, then the oscillation pattern looks something like this. So I'm drawing here the distance to the reactor on the horizontal axis, and it's a log scale. So each tick mark is increasing by a factor of 10. So that's why it looks kind of distorted. But you have this yellow line here corresponding to a fast oscillation frequency, which I'll put in quotes because fast is kind of relative. But then there's also a much slower oscillation frequency in this blue curve. And so if you put your detector around this 1 kilometer mark, what you'll see is really the effect of just this larger of the faster of the 2 frequencies. You'll basically see the electron antineutrinos from the reactors disappear because they're oscillating away, and they should do so at a frequency that's proportional to the larger of the 2 frequencies. But you can imagine putting a detector much further away, and then what you would see is a frequency driven by the larger of the 2, the slower of the 2 frequencies, so the smaller difference between the 2 neutrino masses down here. And then to involve all 3 flavors, what you get is really something like a superposition of both of these effects at the same time. So you have one oscillation superimposed on a slower oscillation. And so experiments are sensitive to different values of these parameters based on these known values. And we can use different experiments to constrain what these frequencies are and what the amplitude of these oscillations are, and build this picture that I'm showing on this page. Okay, so 3 neutrinos, 3 masses, 2 frequencies. This is actually a really successful model of how we've observed the universe. So it's even backed up by a different experiment that's not a neutrino experiment. This is the Large Electron-Positron Collider operating in Europe. It's more commonly known as the LHC, but before it was the LHC, it was called LEP. So it's a 27-kilometer ring. And what's special about colliding electrons and positrons together is that you can really dial in their energies. And when you dial in the energies to specific known values of the particles, you can produce those particles in large quantities. So this was done at LEP. There were experiments that tuned the energies of the electrons and positrons colliding to produce a particle called the Z boson, which mediates the weak force that the neutrinos can experience. So when these electrons and positrons collide, they produce the Z boson. And in this diagram, the time is running from left to right. So the electrons and positrons come in. By convention, we switch the direction of the arrows for the antiparticles, so that's why they look backwards. But time is going from left to right here. So the electrons and positrons come in, they produce the Z boson, and then that Z boson decays. And one of the things the Z boson can decay to is a pair of neutrinos, a neutrino and an antineutrino. And if we look at the distribution of the Z boson decays, what we find is a picture like this. So on the horizontal axis here, this is the mass of the Z boson, reconstructed from the particles that it decayed into. And it has some width to it. When the Z boson decays, we can't see the neutrinos that come out of it, but the width of the Z boson decay is affected by the presence of neutrinos. And one of the things you can do is ask how many neutrinos there are. So even though you can't detect the neutrinos, the shape of this pattern from the decays of the Z boson should be affected by how many neutrinos there are. So zooming in a little bit, you can see at the peak here, there's a case for 2 neutrinos, 3 neutrinos, and 4 neutrinos. And the data from this collider experiment falls really nicely onto the prediction of what the shape of this distribution should be for 3 neutrinos. There's also one other interesting thing about this plot, which is that there's a comment here that the error bars on this are magnified by a factor of 10. So you can barely see the error bars in this on this zoomed in plot, but they're already magnified by a factor of 10. So this is something we know really precisely, that there are really 3 neutrinos in nature. And then this continues on, as I mentioned, in different types of neutrino experiments that we've done over the years. So we have atmospheric neutrinos. We can look at atmospheric neutrinos and describe them very well with 3 flavors that oscillate with 2 different frequencies. We can do the same thing for these long baseline neutrino experiments like T2K, where you look at the neutrinos changing from one flavor to another. Reactor neutrinos, as I mentioned before, and then also solar neutrinos. We can use this model to apply different predictions to all of these different sources of neutrinos, and we generally see that they agree with each other. So this is a very robust model that we've developed. But today I want to talk about where that model starts to break down. So I've titled this lecture series, or this lecture, Mysteries at Short Baselines, and we're going to explain what that means and what interesting things are happening in the world of neutrinos that relate to short baselines. So I want to start with one detector called LSND, the Liquid Scintillator Neutrino Detector. This detector worked very similarly to a long baseline experiment, but with a couple twists. So in previous lectures, we've talked about how neutrino beams are created, where you take a proton and you smash it into a block of material. The pion particle comes out, and then that pion decays into neutrinos. And by focusing those pions, you can make a very focused and collimated beam of neutrinos that travel towards your experiment. So LSND did something a little bit differently. Instead of smashing the protons into a target and then having the pions travel and then decay, they actually put a block of material after the target to stop all the pions in place. So the proton interacts, the pion is produced, but then they put this copper block in front, and the pion stops in the middle of that copper block. Now that pion's at rest in the middle of the copper block, it still decays, but it has a different energy and a different flavor composition than you would expect from a neutrino beam experiment, like the T2K experiment. So when the pion decays, it decays into primarily an anti-muon, so a positively charged muon particle, and then also a muon neutrino. And that muon also decays itself. So it decays into an anti-electron or a positron, an electron neutrino, and then an anti-muon neutrino. And what you can do is place a detector not too far from this source and see a lot of these neutrinos that are coming out of these decays. So LSND, it placed its detector about 30 meters away. And the detector worked on this principle of Cherenkov radiation that I mentioned at the beginning, where the neutrino interacts, produces a charged particle, and that charged particle emits a ring of light that is then detectable on the walls of this detector. So this is kind of the experimental setup. And what is expected from this chain of decays is that you get neutrinos of different flavors. So you get this muon neutrino, you get an electron neutrino, and then an anti-muon neutrino. But crucially, you don't expect any anti-electron neutrinos. So there's no new E with a bar over its head, just because of the way these decays worked. So LSND could actually detect these anti-electron neutrinos if they existed. And the way that worked is by using a feature of the detector material. So in the case of neutrinos, when the neutrino interacts, it produces an electron with a minus charge and also a proton. That proton is usually too low energy to make any Cherenkov light, so it's usually not seen. But that electron produces the Cherenkov light. In the case of antineutrinos, though, you have a positron, which identically looks like the electron in this kind of experiment, because the Cherenkov light doesn't care about the charge of the particle that's producing it. But the key point here is that proton now becomes a neutron. And when that neutron is traveling through the detector material, it will be captured by some of the nuclei in the detector and emit a second burst of light. And so actually, when you have an anti-electron neutrino, you can ask, is there a second flash of light. And if there is, then you know it was an anti-electron neutrino instead of a regular electron neutrino. So this is a picture of what the LS&D detector looked like. It's smaller than something like Super K, for example, but it's appreciable size, and it's pretty close to the neutrino source, so it sees a lot of neutrinos. And what LS&D saw was this. This is a plot showing on the vertical axis something called the beam excess. So what this means is that they took data when the beam was on and the beam was off, and then they subtracted the two and asked what the data was after that subtraction. Then there are a couple different data sets on this plot. So in the black data points, this is what they actually observed. And then there are two different background components here. So these are things that would show up in the beam that are not, or that are expected to have been observed. So in green, these are backgrounds from actual anti-electron neutrinos that were produced in the beam. So this picture I gave you where you don't expect any anti-electron neutrinos, it's only slightly misleading. There are actually a few that are expected, so they account for these. And then there are some other backgrounds from other types of neutrinos that accidentally got misreconstructed as a anti-electron neutrino. So there are two sources of background, and you can see that the data is well in excess of both sources of these. Now, this experiment ran in, I think, the late 90s, where we were really just starting to see the effect of neutrino oscillations in different experiments. So experiments were looking at oscillations, and we didn't really know where the frequency was supposed to be, what these differences of masses were. So LS&D also looked for oscillations too in their data, and they said, okay, well, we have this excess, maybe we can interpret it in the context of neutrino oscillations. So, and they did that, and this is what they saw. So when they fit for oscillations, when they fit the model of oscillations to their data, they got this blue prediction. And so it actually fits the data quite nicely. So you can see that as a function of L over E, which they're plotting in the vertical or the horizontal axis here, the blue or the stack of different contributions to their data, so the backgrounds plus the effect of oscillations, really matches their data quite nicely. There's only one problem with this, which is if we go back to our picture of neutrino mass and how those masses relate to the different frequencies. On the previous page, I showed you that LS&D had an L over E of about 1 kilometer per GeV. And previously, we had talked about T2K experiment, which was seeing oscillations at a scale of about 500 kilometers per GeV. So really, what we're saying is if we treat LS&D as an oscillation effect, is that we have a picture like this, where now there's not just two frequencies, but maybe a third frequency. But that other frequency has to be about 100 times larger than what is observed by T2K or the reactor experiments, because they're observing these oscillation effects at such short distances given their energy. So it's some picture like this, which would be a radical change to the way we think about neutrinos and neutrino mass. So this was a really big deal, and of course, anything that's a big deal in physics needs to be corroborated by a second experiment. So there was another experiment built called Mini-Boon, and it was designed exactly to check if these oscillations, or if what LS&D was observing was due to oscillations. So a nice way to do this is to build a different experiment at a different L over E, and see if you still, at the same L over E, but with different experimental parameters to see if the effect is still there. So in other words, you design a different detector and you put it on a different source of neutrinos so that you can eliminate any potential confounding systematic effects, but the L over E, which is driving the physics, is still the same. So Mini-Boon, it used this giant liquid scintillator detector, and it was covered by walls of phototubes. And it was placed in a neutrino beam that was very pure in either anti-muon neutrinos or muon neutrinos. So different than the kind of mixture of neutrinos that you would get from the LS&D neutrino source. Okay, so here's a picture of where Mini-Boon was located. It happened just about an hour from here at Fermilab. So this is a picture of the Fermilab campus. In yellow here, this is a proton accelerator called the booster. And the protons from the booster follow this path through the Fermilab campus, and then there's a target right around here where those protons smash into, and it produces a neutrino beam through the decay of pions. So instead of having the stop pion decay, like in LS&D, these pions travel for a little bit and then decay, and then those neutrinos make their way in a focused beamline and mini-boon is sitting right in that path. So the way mini-boon works is it detects Cherenkov radiation just like LSND, but the detector design is a little bit different. So in particular, so the Cherenkov radiation is mostly used to separate muon-type neutrinos from electron-type neutrinos. So they have a different source of neutrinos than LSND. They care about different backgrounds. So on the left here, I have this anti-muon neutrino that's coming from the BNB, or the booster neutrino beam at Fermilab. It comes in, it produces a charged particle, the positively charged muon, or the anti-muon, and then a neutron, and that muon makes its way, or produces Cherenkov light, which makes its way to the detector walls and lights up some of these phototubes that are on the walls of the detector. If you had an anti-electron neutrino, and remember we're looking for the oscillation of anti-muon neutrino to anti-electron neutrino, then you would get something slightly different, because that electron that's produced in the interaction would scatter around a little bit. It's a lot lighter than the muon, so it would produce a ring pattern that was much more fuzzy than a muon would. So the muon just kind of travels in a straight line, but the electron scatters around a little bit and produces light that goes everywhere. So your ring is not quite as sharp. There's no way to detect the neutron in mini-boon, but that's okay because because we have a very pure beam of either anti-muon neutrinos or muon neutrinos. So you don't have to separate the anti-neutrinos from the neutrinos in this experiment. So what does that actually look like? It looks like something like this. So this is a ring pattern from one of the candidate neutrino events in mini-boon. This is the light pattern that you would see on the walls of the detector coming from a charged particle produced in a neutrino interaction. So what did mini-boon see? So here's a picture, kind of the same as the LSND version, with the events expected on the vertical axis and then the neutrino energy on the horizontal axis. So this is a big stack of different things, but what you want to pay attention to is this kind of blue line, which is the sum of all of these different sources. And the idea here is that you're going to look for data on top of all these different sources of background that mini-boon identified. So what does the mini-boon data look like? It looks like this. So not a very good fit to what they expected. In particular, as you go lower and lower in energy, you start to get a bigger difference between what you expect and the data points. So this is also pretty troubling, given the context of the LSND experiment. And a natural question to ask is that are the results of mini-boon and LSND compatible with one another? And the answer is mostly yes. So if you try to plot the expected oscillation probability against the mini-boon data, you can pick different frequencies. That's the difference between these green and these purple lines, and you can actually see that it gives you a pretty good fit to the data. And these frequencies that were chosen are pretty compatible with the LSND ones. So in particular, this pink line, this is showing the 0.1 EV squared value of the oscillation frequency, which again is 100 times higher than what was observed, or than what's observed by T2K in the reactor neutrino experiments. So this is really exciting. Maybe evidence of a fourth neutrino. So you have three masses that correspond to two frequencies. We're now adding another frequency, so you have to add a fourth neutrino to make this all work. The thing is that we can't forget what we observed at the Large Electron Positron Collider. So remember this result that I showed earlier, where we're very confident that there are really only three neutrinos. If you want to evade that and still add another oscillation frequency, what you have to do is you have to make sure that this extra neutrino that you're adding doesn't have weak interactions. If the neutrino doesn't have weak interactions, then it wouldn't be present in the Z boson decays that were observed very precisely at LEP. And so what we've termed this neutrino that has no weak interactions is a sterile neutrino. And that's just the name that we give to this hypothetical neutrino that could have an effect on oscillations at this scale, at these frequencies. So now it's important to start keeping track of different experiments. So I've put together a little scorecard where we're going to ask if there's a short baseline anomaly in different experiments. And so far, we've looked at two experiments that fall in the yes column, LSND and mini-boon. They have some kind of thing going on at short baseline. Let's look at other experiments and see how this goes. So the next one I want to talk about is reactor neutrino experiments again. And reactor neutrino experiments see their neutrinos through the decay of the fission products from nuclear reactors. So you have some nuclear reactor, it has uranium in it and neutrons flying around, and those neutrons hit the uranium, causes the uranium to break apart into unstable isotopes, which then undergo decays that produce neutrinos. And so the kind of picture looks like this. You have some heavy isotope. It's hit by a neutrino. It fissions into something lighter, and then those products then undergo decay that produce neutrinos. And reactor neutrino experiments, as we talked about at the beginning, have been successful in looking at the survival probability of an anti-electron neutrino. So in other words, what's the probability of an anti-electron neutrino staying an anti-electron neutrino as a function of distance from the reactor? So the kind of cartoon version of this is shown here. You have the reactor at a distance of 0, but then you place your detector somewhere further away, like 1 kilometer, for example. And then you start to see oscillations turn on as a function of the distance your detector is away from the reactor. And this was very successful, and it was used by many experiments over the years to really hone in on this picture of 3 neutrino flavors and the two frequencies of oscillations that is our modern understanding of neutrinos. So in particular, there are 3 famous ones: the SHO experiment in France, an experiment in Korea called Reno, and then the Diabae experiment that we mentioned previously. So all of these 3 experiments agreed on the measurement of neutrino oscillations that they made using roughly the same technique, a detector placed about 1 kilometer away from the reactor. So let's throw in the sterile neutrino and see what happens. So if we're going to add a sterile neutrino, then the picture changes slightly. Because we no longer have these 2 frequencies, we actually have another frequency that's even faster than the 2 we've had previously. So if we zoom in on this picture that I showed at the beginning, so the probability of finding an anti-electron neutrino as a function of the distance from the nuclear reactor, zooming in to very short distances, we've now added an extra frequency that shows up at very short distances. And what that frequency does is I'm showing in this purple line, it adds an oscillation effect on top that you wouldn't expect from the other 2 frequencies. And that oscillation effect might be too fast for you to actually resolve. But on average, if you just looked at a range of neutrino rates in your detector, what you would see is that the average rate should drop a little bit, even at short distances, due to this sterile neutrino. So in other words, now instead of seeing the probability at 1, you're seeing a very fast oscillating probability that averages out to something like 1 minus a little bit, minus a few percent. So you would expect the rate of the neutrinos in your experiment to drop a little bit based on the presence of this neutrino. So everything was going fine with reactors for a long time, but in 2011, people got around to actually updating the prediction of reactor neutrino fluxes. So it's a very complicated process to try to predict how many neutrinos you should see from a reactor because there's a lot of different nuclear physics involved. So in particular, a lot of the nuclear physics measurements were based on very old data, but there were some updates to that data that got folded into newer models. So the kind of picture in 2011 was something like this. You had all of these different reactor experiments that were measuring the anti-neutrino rate, and they typically fall along this line, which is about 1. So data over prediction is around 1, and this green bar is the average. So you average them all together, they're sitting right where the prediction is. And this prediction accounts for neutrino oscillations. So even though you get out to about 1 kilometer over here with kind of the Reno and Diabae experiments, since this picture is accounting for oscillations, they're still going to fall along this band of 1. But then when the reactor neutrino flux is updated, something interesting happened, which is that the prediction went up a little bit. So now, instead of sitting at 1, all of these reactor neutrino experiments were suddenly sitting a little bit below 1. The average of the reactor neutrino flux measured by all these different experiments was now a little bit too short. And this just came from theoretical predictions, a more accurate calculation of the reactor neutrino flux. So this is very concerning because now you have this pattern in reactor neutrino experiments that looks kind of like what you would expect from a sterile neutrino. So people got very clever because, again, this would be a very important discovery in physics. And what was decided that would be studied is that if you had a true sterile neutrino, then it shouldn't care which radioactive isotope that came from. In other words, the neutrinos from uranium decay, the fission of uranium should be affected the same as the neutrinos from the fission of plutonium, for example. And that gives you a handle because as reactors burn fuel, the fraction of these different isotopes change. So one kind of clever experiment you can do is you can say, okay, what's the rate at the start of the reactor operation, and then what's the rate at the end of the reactor operation after it's burned some of the fuel. And the kind of picture here is that you have this pie chart in a nuclear reactor where you have some fraction of uranium-235 that gets converted into a plutonium-239 as the reactor keeps going. So this fraction changes. And the Diabet experiment designed a test that they could do where they tried to figure out what the relative contribution to the antineutrino flux was based on the fuel content. So this plot on the right is showing the rate expected from plutonium-239, and on the horizontal axis here, the rate from uranium-235. And then the prediction is shown as this black oval here. And what they found is that actually their prediction only falls short in the prediction from uranium-235. So in other words, the model the model overpredicts the amount of anti-electron neutrinos you should see from the decay chain of uranium-235, but it actually gets the plutonium rate kind of right on the money. So if you look just across a horizontal line, this red point, which is the measurement of Diabet, aligns pretty well with the predicted rate from plutonium. So you can kind of design an experiment that separates out these different effects. So the conclusion from this is that we still don't know, but if the model is correct, then this is not a sterile neutrino because the rate deficit only shows up in one of the isotopes. So it could be that the model is wrong and we need to update the model even further, but this is kind of evidence that if the model is correct, then this anomaly could be resolved through some other mechanism rather than adding a sterile neutrino. So we're going to add it to our scorecard in the yes category, but put a question mark there, just because there's a little bit of an asterisk. Okay, next I'm going to talk about gallium, which is another kind of experiment you can do. So gallium is a radiochemical experiment where you have a big tank of gallium, and what's interesting about gallium is that when it's exposed to electron neutrinos, it converts into germanium. And you can actually count that germanium over time. So this was used to really great effect in the 90s. There was a couple experiments called SAGE and GALEX, and they were looking at neutrinos from the sun. And the neutrinos from the sun are all these electron neutrino typed, and so they could make very precise measurements of the flux of neutrinos coming from the sun using this technique. More recently, though, they've switched over to using radioactive sources that produce these electron neutrinos. And so you can put a source of electron neutrinos right by your detector and then see if you get the expected number of germanium after you wait for a little bit. So one experiment that's doing this is called the BEST experiment. It's taking place in Russia, and it's essentially just a big tank of gallium, but inside they put a radioactive source. So if you look at this tank and take a kind of a cross-section of it, it would look something like this. You have a source in the middle that's emitting electron neutrinos, and then they have two tanks of gallium, so one that's very close to the source and then one that's on the outside of the source. And as the electron neutrinos are being emitted, you expect some of that gallium to change into germanium. And that gallium is then flushed into these giant reactors that stir it around. It's actually a liquid at room temperature. And then the germanium is extracted from the gallium in this way. So here's a picture of the germanium counters that are used in this experiment. We call this, so what they measured is actually a deficit, just like the reactors. So they predicted to measure this rate of germanium, but actually the trend of different measurements of this process has found there's actually a deficit, just like in the reactors. So we've called this kind of collection of data the gallium anomaly, where just like in reactors where you expect a sterile neutrino to affect your oscillation measurement at short distances, the same thing can happen, or it looks to be happening with gallium. So another kind of mystery. Okay, I'm now going to switch a little bit and talk about the other side of things. I've told you about the anomalies, but there's two sides to every story. So the one I'm going to bring up right now is the Carbon experiment, which ran in the UK from the 90s just about to 2000. It It was a scintillator detector, and what it did was very similar to what LSND did. So it was also placed at a stopped pion source, and it was trying to measure the rates of different neutrinos. It was designed to make measurements of neutrino interactions with different kinds of nuclei. But when the LSND anomaly was kind of uncovered, they switched to doing an oscillation measurement. So anyway, it's a big tank of liquid scintillator, and it is partitioned into different cells. And by looking at the scintillation light produced in each of the cells, you can figure out what type of neutrino interacted. Does it look more electron-like or more muon-like? And so they repeated this experiment from LSND using a very similar source. And what they found is that there was actually no excess. So unlike LSND, they didn't measure any excess. In fact, they measured 15 events, and they expected about 15.8 events of background. And so interpreting their result in terms of the context of the LSND result, they're actually in conflict with each other. And this plot kind of summarizes that conflict. So the vertical axis here is the frequency, this delta m squared parameter again. And then on the horizontal axis here is the oscillation amplitude. And the blue curve shows what LSND prefers. So any of these values of the frequency and the amplitude would explain their data to a pretty good amount. But the Karman experiment, on the other hand, didn't observe any excess. So what they do instead is they say, well, we're going to exclude all the parameters that would make our data, or that would not explain our data. So the Karman experiment puts these limits in this shaded gray area. So in other words, all the Karman data would be inconsistent with anything in this region. And you can see it overlaps a little bit. The LSND experiment and the Karman experiment were at different baselines, so they don't totally match up. But to a good degree, the Karman experiment disfavors the LSND experiment, but not totally. So there's still some of this parameter space left where you could have a stereo neutrino oscillation. Okay, so updating our scorecard again, we now have one in the no column. So we have these 4 anomalies, and then Karman is a no. But I want to turn back to the mini-boon experiment. So we want actually a better detector to answer this mini-boon question because it has one fatal flaw, which is electrons versus photons. To understand why, we have to look at the distribution that I showed before and kind of break it down component by component. So this is the picture I showed before with the mini-boon data showing an excess over the background, and the background come in different colors. These green colors at the top, these are actually expected anti-electron neutrinos and electron neutrinos from the beam. They don't happen at a very high rate, but there are some there, so they're expected. And they can't really be reduced because they look like the signal you're searching for. All you can do, or the best you can hope for, is to look for an excess of those types. But look at the red and the yellow. What these are actually photons from different processes, different particles that could be produced in the mini-boon experiment. So in red in particular, this is the pi 0. And the pi 0, when it decays, produces 2 photons. And then there's also in yellow something called, I'm calling the delta process. It also produces photons. And why this matters is because photons and electrons look the same in these experiments. So to understand why, we have to look at what happens at a very small scale when an electron interacts in the detector. It does something called an electromagnetic shower. And there are different processes involved in this, but basically as the electron travels through the detector, it can scatter. And when it scatters, it can produce a photon, and then that photon can then go on to produce electrons and positrons. And so so starting from an electron, you actually get a shower of particles that kind of go out from the interaction point. And this creates those fuzzy ring patterns that we talked about before from the Cherenkov radiation. So this is happening at a small scale, but you can take kind of a branch of this process, like the one from the photons, and you can say, well, what if I started with a photon? And you would get the same thing. You would have a photon starting that would produce some electrons that would then go on to produce photons and electrons. And these two processes, whether they start with an electron or a photon, are indistinguishable in mini-boon. So there's a lot of background in mini-boon. And so what if you could design an experiment that would separate these two processes? So just a little bit more about this, just to say kind of explicitly, mini-boon is looking for this process, the anti-electron neutrino producing a positron, which produces a single electromagnetic shower. On the other hand, you can have this pi 0 process, which produces 2 photons. So I've drawn that here as the neutrino coming in. It scatters with a proton, and there's a pi zero, but it doesn't live very long. It has a very short decay time, so it immediately decays to 2 photons. And a lot of the time that looks like 2 rings. So I'm showing this example from Mini-Boon, and you can kind of make out that there are 2 rings. But what can happen is that those rings can overlap, or one could be brighter than the other, so you miss one. And so this contributes a big background to the search that Mini-Boon is doing. And then the delta process. Just quickly, the neutrino comes in. It produces a particle that we call the delta. It's actually just a proton, but kind of in an excited state, so it has some excess energy. So when it decays into a proton plus a photon. And that photon creates an electromagnetic shower, which is the same signature that you're looking for when you look for this oscillation effect. So back to the Mini-Boon picture, just briefly, you can imagine that if you doubled or increased the size of these different backgrounds, if you were uncertain about them at all, then your excess would go away. So in other words, if you don't know this red process very well, and you're uncertain by a factor of 2, let's say, then you would double the amount of red in this picture, and now suddenly the data is explained by all the backgrounds, and there's no oscillation effect. But what kind of detector can do this? So I'm going to talk about tracking detectors, which are a different concept than what we've really talked about for neutrino experiments so far. So we've seen a couple of these. They've kind of shown up in different experiments that we've talked about. So we've talked about the bubble chamber a little bit. This was used in the 50s to first identify charged particle tracks. The way this works, it's a liquid under pressure, and as the particle passes through, it creates these little bubbles that you can then take a picture of with a camera, and you can see those tracks. They stay around for a little bit in the bubble chamber. So a really, really great technology and super important in the history of particle physics. Also in lecture 1, we talked about the experiment that told us that there was that there was 2 different types of neutrinos, an electron neutrino and a muon neutrino. That experiment was done with a spark chamber, where particles leave trails of ionization, and then there's an electric voltage that's applied, and those ionizations, that ionization trail lights up with sparks. And so this is a picture of what that spark chamber would look like. And then as particle detectors became more and more advanced, people got more clever. This last example is called a drift chamber, which is used in a lot of collider experiments. It's basically strands of wires that, as particles pass through, they leave signals on the wires, and you can get a very precise picture of the particle's position from those strings of wires. So just want to mention a little bit about ionization, what it looks like at kind of a very small scale. As a charged particle passes by a nucleus has some electron cloud, it can actually free one of those electrons and leave behind a positive ion and a freed electron. And if you imagine like a big tank of material, then this particle, as it travels through, is leaving a trail of this ionization. So you have free electrons that are now separated from the atoms that they were once part of. And so how do you detect this ionization? So the drift chamber that I just mentioned, the kind of concept about this is that you have 2 planes of wires, and they're arranged orthogonally to each other. So this picture here at the top is showing what you would see if you were looking down at it, but then this bottom panel is showing the same thing, but if you were looking at it from the side. So there's some gap between them, but they're crisscrossed over each other. And as the particle travels through, some of that charge gets deposited close to one of the wires, and that freed electron can then drift towards one of the wires and leave a little signal. And if you have this crisscrossed pattern of wires, then you can, in 2D, 2 dimensions, reconstruct where the particle passed through these wires. So that's the idea, but it has one fatal flaw, which is that if your charge distribution is not ideal, if it's kind of parallel to the plane, then you can have a lot of ambiguity. You can have all these kind of wires lit up at the same time. So even though the charge maybe forms a track, it's really hard to say what the direction of the track is. So there's a lot of ambiguity here. So what if you could see in 3 dimensions? So how would that look like? Well, there was a very clever idea by a physicist by the name of David Nygren, who realized that if you took this plane of wires and didn't require that the charge passed next to it, instead you brought that charge over to the plane of wires, then the time taken for those particles to reach your wires would tell you something about where it was positioned in 3-dimensional space. So now you have each one of these things moving at the same velocity. One's going to arrive first, and you're going to see that signal first, and then the next one will arrive, and then the next one will arrive. And now you can unambiguously tell tell which charge came first and figure out the position in 3D. So it was very quickly realized that this kind of detector could be spun into, or could be made into something that was very practical for physics using a particular detector medium. So the liquid argon time projection chamber became the leading concept for this type of detector. This was first proposed by Carlo Rubbia, who would a few years later go on to win the Nobel Prize for the discovery of the W and the Z bosons. So unrelated to this, this insight, but he picked liquid argon, which maybe sounds a little bit random, for a couple really good reasons. So first of all, if it's liquid, then you have a lot of targets. So unlike a gas detector, the density is much higher in a liquid detector. So you can fit a lot more targets in there, which is really great for neutrino interactions because more targets means more interactions. Also, liquid argon can be made very pure, so those electrons can drift for a long time without being interrupted. So you can build a detector that's quite large using liquid argon because those electrons will just keep drifting through the argon without being deflected or anything like that. The next one is that liquid argon, it's transparent. It looks like a glass of water if you had a glass of liquid argon. So light passes through it very easily. And then also it's cheap. There's argon naturally in the air around us, so you can extract it from the air and just get a lot of it. There's one downside, which is that you have to keep it at 87 Kelvin, which is a little bit cold. So that was one problem. But if you can do all of this, if you can keep it at 87 Kelvin, then here's the kind of detector you can start to build. So I'm showing here a picture of a liquid argon detector. So the blue area shows the liquid argon, and then a row of photomultiplier tubes behind it, and then these wire planes that I talked about before. They're arranged perpendicular to each other. So when you have a neutrino interaction, the neutrino comes in, the particles go out, and immediately what happens is that the argon gets raised to an excited state, and then it de-excites and emits some scintillation light. That scintillation light is just photons, but they're low energy, so they don't create particle showers like we talked about before. And then you also have these freed electrons from the ionization. Those stick around for a little bit. You then apply an electric field and drift them towards those wire planes, like we talked about with the time projection chamber concept from David Nygren. So those electrons start to drift. They drift a little bit more, and then finally they cross your wires, and then you get a signal that comes out. And now what you can do is look at that signal, and there's two reference points here. So you have the time when that scintillation light arrived at your photon, or when that photon arrived at your photomultiplier tube, and then the time that you saw the signal on the wire. And that gives you the timing information that allows you to figure out where that charge came from, how far it was away from the wire planes when it was put in your detector. Okay, and this is a reality. You can actually build these, and these have been built at Fermilab. So here's an actual picture from one of these liquid argon time projection chambers showing a neutrino interaction, and you can just see that the level of detail is kind of unparalleled. The scale here is 75 centimeters, so actually each one of these points is a couple millimeters across. And the way this picture is interpreted is that the neutrino is coming in and then interacting with an argon nucleus here, and then charged particles are coming out of it. So you can really see all the different details. You can see particles that leave very straight tracks, and then you can see particles that make these big showers where like a photon converts into electrons, and then those electrons create more photons, and they kind of spray outwards into this big shower. So this is from the microboon experiment, which is placed at Fermilab in the same beamline as miniboon. So here's the geometry. Miniboon is around here. Microboon is just in front of it. And this collected data from 2015 to 2020. Here's what the microboon experiment looked like. This is the tank that contains all that liquid argon. And then inside is this array of photosensors and these wire planes. Okay, going back to our description of photons and electrons. So this was a key background for the miniboon experiment. But now if we look at it with this liquid argon time projection chamber, what happens? So here's a picture of an electron-neutrino interaction, where an electron-neutrino comes in, produces a charged particle and a proton. And you can very clearly see it in the liquid argon detector. Now if we look at a process, so yeah, just to label it a little bit, let's see, okay. Right, so we have this electron that's creating a shower, and then you have a proton, and then this electron goes on to produce an electromagnetic shower, like we said before. Looking at the case for a photon, it now looks very distinctly different. And the reason is that now there's a gap between where the neutrino interacted and where the shower started. Because the photon is a neutral particle, it doesn't leave any ionization, even for a few centimeters in the detector. And so then the shower only starts after a few centimeters. So labeling this one, it looks like this. The proton is going out from the interaction point, and a photon is going out from the interaction point, but it doesn't leave any charge before it converts to an electron and then creates the shower. So looking at this gap allows you to separate electrons and photons now that mini-boon could not do. So going just quickly through the microboon data, this was data that they published in 2022. What you're seeing now is a picture of the expected backgrounds on the microboon experiment and the data overlaid on top. So this green area is the number of electron neutrinos that are expected without oscillations, so just intrinsic to the beam. And you're looking for an excess on top of this. And clearly there is no excess. But this kind of distribution should be compared to the mini-boon distribution from before, where before at these low energies we had very high background contamination from these processes like the pi-0 decay and the delta process. These are now gone from the microboon experiment because of this photon-electron separation that they can do. And just to drive the point home, the red line is showing what you would expect from the mini-boon experiment if the mini-boon excess were present in the microboon experiment. So clearly the data is not favoring the mini-boon excess. So we have to update our scorecard. We have one more in this no column. We have the microboon experiment very recently as of 2022. Okay, but that's not the end of the story because there are two big mysteries that are still out there. So the first one is that microboon didn't see this excess, but what caused it in the first place? We still don't know the origin of the mini-boon excess. And then the second one is that microboon doesn't really have enough data to fully cover all these other anomalies that are out there. It's looking at the mini-boon anomaly, but there's still this reactor in the gallium anomaly. And so you really need, if you really wanted to test the sterile neutrino hypothesis with these kind of detectors, you have to do something a little bit different. And that's where the short baseline neutrino program at Fermilab comes in. It's actually a series of 3 detectors that are all based on this liquid argon technology to give you really precise imaging of all the different interactions. So there are 3 detectors here. The first one is microboon, which we've talked about. It was kind of the trailblazer experiment. So it established the liquid argon time projection chamber design, and then it probed this electron versus photon question for the mini-boon experiment, or that was based on the mini-boon excess. And that collected data from 2015 to 2020. Then there are 2 other detectors which are just coming online in the past couple of years. There's the short baseline neutrino detector, which is a really advanced iteration of the liquid argon time projection chamber, and then the Icarus detector, which actually came to us from Italy and then went to CERN, which I'll talk about in a second. But the combination of these 2 detectors really works together because SBND is very close to the beam, and Icarus is a little bit further, kind of at the same level as mini-boon, the same distance. And so SBND is hoping to see oscillations turn on if they exist before they're at their full extent in the Icarus detector. So you can use both detectors together to really map out the space of sterile neutrino oscillations if they exist. And then SBND is also being very close to the detector. It will have a lot of statistics, a lot of neutrino interactions that will be very helpful in constraining different model uncertainties that go into these analyses. So just back to this map a little bit. Again, we have the booster neutrino beam over here where the target is. SBND is right there. It's about 100 meters from the target point. And then Icarus is just behind where mini-boon was, over here. So I'll talk a little bit about Icarus. This is a picture of the inside during the Icarus assembly. You can see kind of some of the components coming together. These are the photodetectors on the walls, and then there are wires in front of it, but you can't really see them because they're so thin. Now, Icarus, as I mentioned, moved over from Europe. It was actually carried by ship, which is a thing particle physicists like to do, is to move their detectors around the world. So it was moved from Italy over to CERN, where it was refurbished for a little bit, and then it sailed over to the US on a ship. It was unloaded in Indiana and then driven to Fermilab from there. It was then installed in Fermilab in, I think, 2018. So here's a picture of it coming into Fermilab, into the building where it would then take data. And then it was hooked up to all these systems that were required to keep the liquid argon at the correct temperature. So that started taking data. The other experiment is the short baseline neutrino detector experiment. This was built a couple of years later, mostly during COVID, actually. So here's a picture of the assembly of one of these wire planes, and you can see really the kind of reflection off the wire planes here. It's very they're very thin wires that are placed very precisely, very precise distances. This was then not moved very far, but it was brought from one side of Fermilab to the other. So here it is on a forklift here being moved into position into the building, and then finally into the place where the liquid argon, where it could be filled up with liquid argon. So it was mounted to this crane and then lowered into this tank. So SBND, I just want to finish with a little bit of information about it. So as I mentioned, it's very close to the beam, and it's expecting about 2 million neutrino interactions per year. So just a huge number of neutrino interactions. And then the other interesting thing that it's doing is using this cold temperature to its advantage. So I mentioned that the liquid argon being at 87 Kelvin is kind of an annoying thing. You have to keep the temperature very low to have the liquefied argon. But actually, SBND is putting the electronics in the liquid argon itself. And what that does is keep the electronics very cold so that the noise on the electronics is at a minimum. And then it has an advanced light collection system that it's using for very precise timing information. I want to talk a little bit about how we're processing the data from SBND by giving a little example of machine learning. So this is kind of a cartoon that's seen very often. You have maybe a picture of a cat, and then you process that cat through some different kind of layers that extract features of that image, and then you run it through a network where the different features of the image are weighted in different ways. And at the end, if you've trained these weights appropriately with a labeled data set that has the truth information to it, so it has a kind of a concept of like, okay, you tell it that this is a cat, or this is a dog or whatever, it will eventually learn the correct weights to apply at this stage. So you can have your picture, and then at the end, it will tell you something like, well, 80% probability it's a cat, 20% it's a dog. This kind of technology has really risen to the forefront and is being used in lots of like AI applications throughout our everyday lives now. You can do the same thing with neutrinos, it turns out, but our data looks a little bit different. So here's a picture of a neutrino interaction in SBND. And using the time projection chamber technology, we really have a full 3D map of what this interaction looks like. But we can do the same thing. So we can have a neutrino interaction, and then we can train a network that will then tell us, is the neutrino an electron neutrino or a muon neutrino, for example. And so it can look at features of the hit patterns in the data that we're collecting, and we can train this network to use AI techniques, which have a lot of great improvements in terms of the accuracy that we can make the predictions and also the speed that these algorithms can run. We're planning on running this actually not too far from us. This is a picture of the Aurora supercomputer at Argonne National Lab, so about 30 minutes from here. It's one of the fastest supercomputers in the world. And we've partnered up with Argonne to run some of our processing for the SBND experiment here. And Aurora is just kind of a crazy amount of computing power. So it has 20,000 CPUs and 60,000 GPUs, graphics processing units. And it contains over 10,000 terabytes of memory. So it has 10,000 of these kind of computers inside of it, and they're all chained together to do computations really fast. So we're really excited to be able to use this for part of the SBND experiment. Okay, and then I just want to finish off with SBND's first data. So this experiment is actually running at Fermilab right now. And it's producing already a lot of beautiful images of neutrino interactions that we hope to do a lot of great science with. So look out for SBND first physics results, hopefully in about a year, let's say, coming soon. And with that, I'll just summarize, but I won't read this off. So thank you very much for your attention.